Hello everyone. So today we are going to see the next part of water treatment, which is sedimentation. So basically, like in previous lecture, we studied the basics of sedimentation, right? Now in this lecture, we will be studying how to design and the numericals for that. Okay. Now, yeah, let's see. For some quick revision, so you know, right, like what was your uh, so yeah, yeah. So in the previous lecture we saw what was the settling velocity, and we calculated its value, and it was in general velocity is distance per unit time, right? And we saw that the settling velocity was uh, rho p minus rho into d square into g upon 18 mu, right? So this is what the settling velocity was. Now we'll see further. So in today's class we'll be seeing the continuous flow tank. So continuous flow tanks are of two types: horizontal and vertical. And horizontal, we have the rectangular, uh, that is longitudinal flow, and then we have circular, that is radial flow. Okay, so let's see the first one, which is rectangular flow tank. So here you can see that, let's see the different design parameters here. So so you see, this is the side elevation of the tank, and what you will be having is the inlet. So the raw water is coming from the inlet, and then this is the length. And if I see the plan view, so the plan view will be something like this. This is the length, and this is the width, B. Okay, and this is the depth of the tank, right? So depth of settling zone. Okay, so this is the water surface, and then from here you will be getting the outlet water, and then this is the sludge zone, this is settling zone where settling is happening, and this is the flow direction from inlet to outlet. So we have different zones here: inlet zone, settling zone, sludge zone, outlet zone. So the important dimension we have is length B, and width and depth, and then surface area, right? Cross sectional area, we'll be seeing everything. And then you see that water flows horizontally from inlet to outlet. That's why it's horizontal flow tank. And then settled solids are collected in the sludge zone. We already know that, and removed from the sludge outlet. And then clarified water will be collected from the uh, out the outlet point. Now let's see some key design parameters. So the very first one is surface overflow rate. Okay, so the surface overflow rate is flow rate divided by surface area. That means, so surface overflow rate is nothing but the velocity. We'll be using it as V naught. Okay, so V naught. Now, if I want to give, this is V naught is equal to whatever discharge came and whatever is the surface area. Okay, so Q is the discharge, AS is the surface area. Okay, so so the surface area is nothing but So from on this surface only water is going. This is L, this is B. Okay, so surface area is L into B. So if I want to know V naught, then it is simply Q upon LB. Okay, so this is your surface overflow rate. Okay, so and the particle whose settling velocity is greater than the surface overflow rate can theoretically be removed. So we know the settling velocity of particle. So that if that settling velocity is greater than surface overflow rate, then particle will settle down. Okay, and we have some criterias for this also, like how much the surface overflow rate should be there. So the range for surface overflow rate comes out to be 12,000 to we have 18,000 liter per meter square per day, and it is for plain sedimentation. Okay, and if I have the sedimentation with the coagulant, then it should be 24,000 to 30,000 liters per meter square per day. For what? For sedimentation with coagulation. So I'll write here with coagulation. Okay, so this is the surface overflow area rate specifications. Now let's move on to the critical settling velocity that we have to calculate. So the critical settling velocity is the minimum settling velocity a particle must have to just be removed from the sedimentation tank. So it should be the minimum. So if the particle has uh, a long velocity, high velocity, it will definitely come down. But I want to know the minimum velocity at which the particle will settle down. So that is critical settling velocity. Okay. So for example, see here, this is the surface area and this is the inlet. So let's see from here the particle is going. Now if in case the settling velocity is greater than V naught, that means surface overflow rate, because water is also flowing. That's the surface overflow rate is nothing but the rate like velocity of water that's flowing. So if particle velocity is greater than velocity of water, it will settle, right, and it will get removed. And if settling velocity is just equal to the surface overflow rate, particle will just settle. This is critical condition. And if the settling velocity of particle is less than overflow rate, it will be getting carried out with to the outlet and it will go out. Okay, so this is the basic understanding behind the surface overflow rate and settling velocity. Now we have some critical conditions. So the critical condition here basically is this one. Vs is the settling velocity in centimeter per second or meter per second. Surface overflow rate is in centimeters per second or meter per second. Q by A, simply A is the surface area. This you have to remember. Okay. Now V Q naught upon AS. So yeah, I think we got what we should get from this. Now let's talk about the detention time, also known as, like we tell it we denote it by T. So here we have that T is nothing but, can I say, V upon Q, right? V is the volume here. Okay, V is the volume. So it's nothing but volume upon discharge. If I see the units, so volume is meter cube, discharge is meter cube per day. So it will come meter cube to meter cube cancel out. It comes in day. So that's how its detention time units with that. So the volume of the tank will be L into B into D, right? So the detention time will be L into B into D upon Q. Yes, so with this we can calculate the detention time of the tank, right? The range for detention time. So the range is 4 to 8 hours for plain sedimentation tank, and uh, around 2 to 4 hours for coagulation added sedimentation tank. Okay, so this is the range for detention time. Now let's move further. So we have the relationship between detention time and overflow rate. How can we calculate that? So you have overflow rate, which is V naught is equal to Q upon L into B, right? And then you have detention time, which is L into B, L into B into D upon Q. So if so from these two relationships, I can say that this becomes V naught, right? So uh, from here I can say that T is nothing but V naught, uh, not V naught, D upon V naught. Like from the first relation, can I say that Q is equal to V naught into L into B, and I can put it here. So T becomes L into B into D upon V naught into L into B. So this L into B and L into B gets cancelled out, and I get T is equal to D upon V naught, right? So this is the relationship between surface overflow rate and the detention time. Okay, D is the depth of the tank, right? So this is how we get the relationship. And now let's see the next thing, which is horizontal velocity of flow. So I have this horizontal velocity is from inlet to outlet. What is the speed of the water that's coming from here and going from that outlet is the average velocity, and that we call as horizontal velocity. So you can see from inlet the water is coming and then it's moving in this direction and then it's going into the outlet. Now the key points are that water moves horizontally from inlet to outlet, and then horizontal velocity depends on flow rate, width and depth. So this is horizontal movement, and then it depends on flow rate, so the discharge, and how much is the width of the tank and what's the depth of the tank. So these things on the horizontal velocity depends, right? Now excessive horizontal velocity may cause short circuiting and disturb setting of particles, right? So if horizontal velocity is too much, then particle will be forced to move with that water, right? It will not get its time or its needed force or like a settled area, the surroundings, so that it can get settled, right? So we should have a minimum horizontal velocity, like in the range, so that the particle it helps the particles to settle down, right? So the typical range for horizontal velocity is zero point 0.2 to 1 meter per second, right? You saw that surface overflow rate is what it was, something 4 to 8, detention time of the tank was 4 to 8 hours, right? And the surface overflow rate is around 12,000 liters per day per meter square. Here the horizontal velocity, so the units are different. You can convert that liter per day into the values of meter per second. But here the horizontal velocity range is zero point 0.2 to 1 meter per second. Right. So it depends on tank design and water quality. Okay. Now the formula for horizontal velocity is VH is equal to Q upon AC, and C is the cross sectional area. So if I see this is if I take one cross section, so this is one cross section of the area, and this cross section uh, we are showing here, right? So this is the cross section, and its area is B into D. So the cross sectional area is B into D, right? So the horizontal velocity becomes q upon b into d, and the overflow rate was q upon l into b. Here q upon b into d, right? So this is the difference between horizontal velocity and surface overflow rate. So the yeah, so here we have mentioned everything what uh, every symbol means. So yeah, we can move to the other topics, which is important design relationships. Okay, so if I want to like summarize everything whatever we studied, so we have q, that is nothing but v naught l into b, right? And then we had t, which was l into b into d upon q, right? And then we had v naught is equal to q upon lb, and then we have vh, which came out to be q upon b into d, right? And from this we also calculated that t is nothing but d upon v naught. So these are the relationships that are very important for designing a sedimentation tank. Okay, so design of sedimentation tank. So these are the relationships. So 4 or 5 equations that we should know while we are designing the sedimentation tank. So it is nothing that tough to like mug up. If we know the concept behind that, it will be easy for us to like we understand the things. Now we don't have to mug up other things that much. A few of the important criteria are also there. For example, the length to width ratio should be approximately or equal to 4, right? It should be greater than or equal to 4. One recommendation is that L by B should be equal to 4. And then we have another recommendations like the freeboard should will also be there, right? Freeboard. So this freeboard is approximately 0.3 to 0.5 meters. This much freeboard we give. And then the sludge zone was there, right? At the bottom of the tank. So this sludge zone is approximately 0.8 to 1.2 meters. So these are some more specifications that we should know. And yeah, with this we come to approximately an end with the horizontal tank. Now we see the circular rectangular tank we saw. Now we have the circular sedimentation tank. So if I want to see the plan view, so this is the plan view of the tank. You can see. So it's so we have here the central inlet. So it's inlet, okay, and then we have rotating machines. So we'll be having rotating machine also, and then we have this radial outlet, okay, and then peripheral launders, and then we have so this is what the circular tank looks like. So at the center is the inlet, and then water travels radially, and with that like suspended particles uh, uh, settle down, and then at the like out at the radial distance there will be outlets, and from the outlets the water will come out, okay. So this is the circular sedimentation tank. So if I want to see the sectional elevation, so we have peripheral launders, we have the outlets. So here clarified water will come. So from inlet you will see the dirty water will come, and then while it's traveling horizontally till here there will be settlement of the sludge, okay. So and then we have sludge scraper arms also that will scrape the sludge, and then yeah, so this is how horizontal sedimentation circular sedimentation works basically. So it also has the horizontal flow, okay. So the flow pattern is water enters at the center and flows radially outward. Clarified water is collected over the peripheral layer, okay. Now so it's simple and economical in construction, suitable for large capacities, and we can have a uniform flow distribution, and it's efficient way to remove the settled solids. So we have inlet zone, we have settling zone, we have sludge zone, we have outlet zone that we know, right? So it's the similar thing to that, but only the working is going on like exactly as was there in a rectangular tank, but it's made or built different than rectangular one, right? So um if I want to compare with the rectangular to circular, so we see here we have longitudinal flow, here we have radial flow. So inlet is at one end, but here the inlet is often at the center. Outlet is at opposite end, right? But here it's the peripheral outlet. Everywhere the outlet will be there, water will be collected. And then we have come to the last one, which is vertical flow sedimentation tank. So it's working a bit different. So in this, the water flows vertically upward and settled particles are collected in the sludge hopper at the bottom. So you can see the water, you have the water which is, so inlet distributor are something like that and outlet is there. So we will be allowing the water to flow upward. Okay, so while it is flowing upward, the particles will settle under the effect of gravity and water is flowing. So once the water is going upward, at the outlet it will taken out. Okay, so this is the distributor and then sectional view you can see. So raw water enters from the top and is uniformly distributed, and then water flows upward in vertical direction. Heavier suspended particles settle by gravity, and then clarified water overflows the outlet weir and leaves the tank. Okay, sludge is withdrawn through the sludge outlet at the bottom. So it requires less floor space, suitable for small flow rates. Short circuiting must be avoided in this. So less area, simple construction, suitable for small. So disadvantages, it's not suitable for large areas, more head loss will be there, or proper distribution system requires in this. So this vertical sedimentation tank is not used that much, that's why we are not going into detail, but just we should know that there is something called vertical flow sedimentation tank, and that we know. So with this we have come to the end of the theory for sedimentation. Uh, in the next lecture, let's see what we are going to proceed with. Basically, maybe we'll be proceeding with coagulation and flocculation.